Hello friends, welcome to my channel. In this video I will cover gate paper solution, thermodynamics and heat transfer subject I will cover. This is second shift 2017 paper. The emissive power of a black body is P. If its absolute temperature is doubled, the emissive power becomes how much? In second case, emissive power, how much we have to calculate. Emissive power formula is E equal to emissivity into sigma A T to the power 4. This unit is watt. This is also important unit. So here it's a black body, so this is emissivity is 1. In second case, E1 is P sigma A T1 to the power 4, and second case T1 2T. If first case T equal to T1, second case T2 is 2T, it's doubled. So second case we have to calculate emissive power sigma A T2 to the power 4. T2 value is double of first one, so 2 to the power 4, 16 into sigma A T to the power 4. Sigma A T to the power 4, here sigma A T to the power 4, its value is P, so it's 16P. D is the answer. This is 1 mark question. Also this is important for ISRO examination and IES. Also for Vizag Steel MT examination also they are asking this type of questions. A mass M of a perfect gas at pressure P1 and volume V1 undergoes an isothermal process. The final pressure is P2 and volume is V2. The work done on the system is considered positive. If R is the gas constant and T is the temperature, then the work done in the process is how much? Work done we have to calculate. Mass is M, initial condition, final condition. Initial is 1 and final is 2. Initial pressure is P1, final pressure is P2. Initial volume is V1, final volume is V2. Temperature is T1, T2. And this is a isothermal process, so T1 equal to T2. Work done we have to calculate. Here work done on the system, it's considered as positive. So work done W1 to 2 process minus integration of PdV. For isothermal process, PV to the power 1 is constant. P1 V1 equal to P2 V2 equal to C is the constant, and P equal to C by V. Put the value of P. W12 is minus C by V dV 1 to 2. So minus C value is P1 V1, then integration of dV by V ln V2 by V1. So you will get minus P1 V1 ln V2 by V1. And from here V2 by V1 equal to P1 by P2. So you can write it as P1 V1 ln P1 by P2, or PV equal to MRT if you apply MRT ln P1 by P2, or mRT ln V2 by V1. So from options we have to check which one is satisfying. P1 V1 B is satisfying. Minus P1 V1 ln P1 by P2. Consider a laminar flow at zero incidence over a flat plate. The shear stress at the wall is denoted by tau W. The axial position x1 and x2 on the plate are measured from the leading edge in the direction of flow if x2 is greater than x1. Then we have to find out tau W at x1 and x2. Which one is greater? That we have to find. Their relation we have to find. So apply Blasius equation. Say flat plate. Let this is position 1 and position 2. This value is x1 from leading edge. This is x2. Already given x2 is greater than x1. So shear stress is denoted by tau W. Blasius equation you apply here. Blasius equation for laminar boundary layer. Local screen friction coefficient. Local skin friction coefficient. CFX 0.664 by REX root over. And REX Reynolds number, local Reynolds number rho V x by mu, or you can write it as V into x by kinematic viscosity. So here 0.664 divided by Vx divided by kinematic viscosity root over. This is equation 1. And again local skin friction coefficient is tau W divided by half rho V square. So this is equation 2. From equation 1 and 2, 0.664 divided by V into x kinematic viscosity root over equal to half rho V square. So from here rho W is inversely proportional to x root over. In this case given x2 is greater than x1. So W1 is greater than W2. Wall shear stress. So from option we have to check C is the answer. Shear stress at the wall. Heat loss from a fin is 6 watt. The effectiveness and efficiency of the fin are 3 and 0.75 respectively. The heat loss in watt from the fin, keeping the entire fin surface at base temperature, is how much? So fin heat transfer. Heat loss or Q actual, it's 6 watt. Effectiveness given, it's 3 and efficiency 0.75. Effectiveness is the ratio of heat transfer rate to the heat transfer rate without fin. Then efficiency is actual heat transfer, Q actual divided by maximum heat transfer. So here Q actual divided by heat loss, keep entire fin at base temperature. So put the data. Efficiency given 0.75, Q actual also given 6 watt divided by Q maximum. So Q maximum we have to find out 6 by 0.75, 8 watt. So here 8 watt is the answer. 1 mark question. Question is, a calorically perfect gas specific heat at constant pressure 1000 joule per kg Kelvin enters and leaves the gas turbine with the same velocity. The temperature of the gas at turbine entry and exit are given 1100 Kelvin and 400 Kelvin. The power produced also given 4.6 megawatt. Heat escapes at the rate, heat rejection rate given 300 kilojoule per second through the turbine casing. The mass flow rate we have to find out. Steady flow energy equation we have to apply. Gas turbine. So Q loss energy in, energy out or exist. Steady flow energy equation SFE we have to apply here. M dot into H1 plus V1 square by 2 plus GZ1 plus Q dot to M dot into H2 plus V2 square by 2 plus GZ2 plus W dot. Just put the value, then you will get your answer. Here data given are Cp equal to 1000 joule per kg Kelvin, T1 1100 Kelvin, T2 400 Kelvin, power or W dot 4.6 megawatt or 4.6 into 10 to the power 3 kilowatt. V1 equal to V2 velocity. Assume Z1 equal to Z2. Q rejected or Q loss. (300 kilojoule per second). We have to find out M dot. So energy in equal to energy out. So this is cancel. Z1 Z2 cancel. Then M dot into H1 minus H2 W dot minus Q dot. Q is loss, so this is minus. Right side it will become plus. W dot given 4.6 into 10 to the power 3 plus 300. So here we can write M Cp dt, M dot Cp T1 minus T2 4.6 plus 4.6 into 10 to the power 3 plus 300. Put the values. If you put the values, finally you will get 7 kg per second. So from option you have to check B is the answer. 1 mark question. Sorry, this is 2 mark question. Negative is here 0.66. A metal ball of diameter 60 mm is initially at 220 degrees Celsius. The ball is suddenly cooled by a air jet of 20 degrees Celsius. The heat transfer coefficient is 200 watt per meter square Kelvin. The specific heat thermal conductivity and density of the metal ball are 400 joule per kg Kelvin, 400 watt per meter Kelvin and 9000 kg per meter cube respectively. The ball temperature in degree Celsius after 90 seconds will be approximately how much? Transient heat conduction and metal ball spherical shape. Metal ball spherical shape. Shape is spherical. Data given. Diameter D is 60 mm. So radius R, it's 30 mm. Initially at 220 degrees Celsius. So Ti is 220 degrees Celsius. T infinity air jet temperature 20 degrees Celsius. Heat transfer coefficient H 200 watt per meter square Kelvin. Specific heat Cp 400 joule per kg Kelvin. Thermal conductivity K same watt per meter Kelvin, 400 watt per meter Kelvin, and density is 9000 kg per meter cube. Time also given, time T, it's 90 seconds. So put the formula T minus T infinity. T value we have to find out. After 90 seconds, T minus T infinity e to the power minus h as divided by rho v Cp into T. E is here. So same we can write it as ln T minus T infinity divided by Ti minus T infinity minus HAS divided by rho v Cp into T. So this also we can write it as theta by theta I e to the power minus HAS rho v Cp T. Theta is final temperature difference T minus T infinity. Theta I is initial temperature minus air temperature or minimum temperature. T minus T infinity is 20 here. It's 220 minus 20, 200. So LC also we can write characteristic length LC is V by A, surface area, volume by surface area, spherical shape, so 4 by 3 pi r cube divided by 4 pi r square. R by 3 we will get. R value is 30 mm by 3 divided by 10 to the power 3. Unit is meter, so 10 by 10 to the power 3 meter. So put the value. We have to find out HAS divided by rho v Cp whole into T. V by AS is characteristic length, so H into T by rho LC Cp. Put the values. H value is, it's 200 into T is 90 seconds divided by density, it's 9000 into LC 10 by 10 to the power 3 into Cp value. Cp value is 400. So if you solve this one, you will get 0.5. So here we will get t minus 20 by 220 minus 20 equal to e to the power minus 0.5. If you solve this one, t minus 20 equal to 200 into e to the power minus 0.5. T equal to 141.3 degrees Celsius. So from option A is the answer. 2 marks question. This type of transient heat conduction or unsteady heat transfer, this is very important. Also in ISRO they are asking this type of questions. Without calculator also you have to solve in ISRO. So this is very important. For other examination also this is very important. One more thing is important here. Time constant. Thermal time constant. This is also some PSU or ISRO they are asking. Thermal time constant tau T. It's rho v Cp divided by HAS or rho LC Cp divided by H. Thank you friends. Thank you for watching my video. Thank you.